We are now going to have a seminar by Professor Dr. Yogesh Joglekar. And before he says that it's a substitution lecture or something, let me say that he has been a part of the endeavor and it's as much from the original soundtrack. So there's no substitution or anything, you know. So Yogesh hails from Indiana University, Purdue University Consortium in Indianapolis. And he, of course, he had first obsession and now passion for PT symmetry. And his other interests include lattice models, quantum Hall effect, graphene, memristors, photonics, as of late, I guess. And he would like to share his excitement on his recent Nature endeavor on, unitary and non-unitary photonic simulations of molecular quantum dynamics. Yogesh.
Thank you for the opportunity here. I am merely substituting for a good friend of mine, Anthony Lang from University of Bristol, who could not join this, this meeting. And so what I'm going to tell you today is some interesting work that we have been doing for the last maybe 3, 4, 5 years. And the idea is, if you have a photonic simulator, which is usually a unitary device, then how do you study behavior of molecules, or more specifically, vibrational behavior of molecules? And to study the processes which are unitary, which is somewhat simpler to do because you have a unitary simulator, and also non-unitary processes such as thermalisation or dephasing and things like that. Okay. So this is work which is a collaboration of a number of people. These are mostly Anthony's slides, and I have made some changes to it. So if you have really hard questions, then I will give you his email address, okay? Yeah. But the work in Bristol has been funded by a lot of things. This has been a collaboration between Bristol, I am at IUPUI, NTT in Japan is the corporation, or their research division is the one which made the device, which was quite a bit of work from what I understand. And Nokia and Bell Labs are where former students of Anthony group are now, basically, who were part of this work. My work itself has been funded by sort of NSF, which has been quite lenient in terms of what I work on versus what I proposed I will work on, basically. Okay. All right, so the idea is that we want to study the properties of vibrating molecules. And it's an extremely complex problem if you want to do it fundamentally. And so what we will do is only study the vibrational modes of this, or simulate the vibrational dynamics of these molecules. And to do that, we'll use an integrated photonic chip, basically, where you are able to map the vibrational modes, which are bosons, into photons, which go into these waveguide arrays. Okay? And so here is the sort of brief outline of the talk. First, I'll provide some motivation, which is, why would you want to do this? And that is sort of based in the idea that you want to do chemistry, making molecules, breaking molecules, making them in different reaction pathways, or to break them also via different specific reaction pathways, and things like that. But if you try to do it in a naive way, it doesn't work. And so I'll provide some background regarding how the field of so-called femtochemistry, where you are using really, really short laser pulses to probe, either excite or to dissociate molecules, individual molecules at very fast scales, okay? And so that is sort of the background. The next part is, in some sense, all we are studying here are bosons, and in some approximation, they are non-interacting, so why bother, right? And so I want to tell you about something which I learned during a sabbatical in Bristol, which is that even bosons which are non-interacting is actually a hard problem, okay? And so what do I mean by hard is something I will talk about, so-called boson sampling problem, or to calculate distribution when you have multiple bosons which are coherently propagating in some system, then what happens? Okay? Then I'll tell you about the device which allows us to do this sort of simulations where we can simulate, let's say, the process of putting in two excitations of, let's say, this bond and two excitations of that bond simultaneously. So in other words, you have 4 photons, identical, 2 identical photons being put in here, 2 identical photons being put in here, and then you are studying what is happening to the dynamics of this molecule, for example, okay, right? And then so after describing this experimental device, I'll just tell you the results regarding different unitary simulations which we carried out, and non-unitary simulations, which is sort of a major topic of interest here, because one of the things that I talked about on Monday was essentially using this chip to then also study how PT simulations can be carried out, okay, or simulations of PT Hamiltonians. And if you want details, these are in this paper which was recently published. Okay. All right, so we'll start with the background, which is chemistry. And I must confess that I was terrible at it, basically. So when I was in school, and I continue to be, but I think I have a better appreciation for the complexity of this field as I learn more, basically. Okay? And so the idea is that you have molecules, and ever since lasers were invented, initially chemists were really excited because they thought, you know what, I know the different bond energies. So if I could just take a laser and match the energy output of the laser to the specific bond energy, I can dissociate molecule along a particular bond. Okay. Turned out it was a simplistic idea because if you try to do that, if you try to shine laser with a specific wavelength into this bond, what happened was that essentially that energy very quickly got distributed into other modes of this particular molecule, and then you did not get bond breaking. Okay. Now, this is so in other words, tuning the laser frequency to the molecular bond frequency, it does not really work in the simplest idea that you would think about. Okay. Well, you could say, well, maybe what I need to do is shape this pulse. Okay. Have some specific relation of the amplitude and the phases of the time-dependent electric field, which I'm going to use to shine on a particular bond and see whether that works. That led to some success, if you wish, where these are all sort of examples of fluorescence, okay, as a function of different pulse shapes that you are doing, and then you try to maximize or minimize the result of you want, what output you want, because remember, when a bond breaks, or specific number of bonds break, then you are going to get, in some cases, products. And so you might be just optimizing what are the products at the end of the reaction that you are doing in this case. Okay? It turns out doing this led to some advancement, but it's still not quite simple because essentially we don't have a good way to understand how to shape this in some feedback way, in some learning way. How do you optimize this problem? Okay? Right. And the idea is really that you want to understand the dynamics of these different vibrational modes and their interference to be able to understand how you could locally excite some bond or some stretch, and then what effects it has on breaking of a particular other bond. Okay? And knowing that, really you need to understand the behavior of bosons, which are non-interacting bosons, let's say, in harmonic approximation, but you want to understand what's the behavior of these bosons and how to sort of, optimize that, okay? Now this evolved quite a bit in the last, I guess, last 10, 15 years is when a lot of progress has been on this area. So one of the things that people had tried in the past was this so-called adaptive feedback control and learning algorithms, which you are using to shape the laser pulse, which gives you better and better outcome. So a crude example of, a crude picture of what is actually done, which is quite sophisticated and hard, is basically you're shining the light onto, let's say, this chemical, which is being dissociated into either this product or that product, basically, okay? By shining laser light at particular shape. You do the experiment, get the data, from that, do the modification of the laser pulse. And doing this in some adaptive way, try to optimize whether you get this pathway or that pathway or different pathways. And this was done, what, now 20 years ago, I guess, right? So there's been significant sort of, I guess, there's been significant progress in also understanding what happens to, or in understanding and being able to coherently excite specific vibrational modes then at very small energy scales, or very small time scales, or basically the scales which are relevant with vibrations of the molecule. So these are sort of, examples which show that. The first one talks about fluorescence of a molecule, where what you do is you shine 2 laser pulses on it, basically, and there is a time difference between, or time delay between those 2 pulses, which are shot at a particular bond. Those 2 pulses are either shot in phase, that is phi equals 0, or out of phase, which is phi equals pi. And that is a function of the delay between those 2 pulses. And this is experimental data. And what this basically shows, the red and the blue curves are separate from each other, means that you are getting different results, this experiment, based on the coherence between these 2 laser pulses, basically, or more specifically, the phase between these 2 pulses. Okay? And that is lasting almost all the way up to, let's say, 100 femtoseconds or so, which are typical characteristic frequency scales of these vibrational excitations. Okay? So in other words, you have tremendous control over vibrational wave packets. This one is another experiment where you have acetylene, which is basically C2H2, and then you try to take out one hydrogen, H+, or dissociate 2 of them. And then when you do that, then it dissociates in 2 different ways, because C2H2 is basically like 2 H's on the outside and 2 C's on the inside. It's like a bar, okay? And so the question is, there's some asymmetry of how much hydrogen output you get in one direction versus the other. And that asymmetry is what is given here, basically, okay, in the output as a function of this. And you can tune that based upon the phase between the laser excitations which are used to excite these or to dissociate this particular case, okay? This is another example where basically they were able to literally very well probe what is the cloud distribution on a femtosecond time scales and things like that. So bottom line is that you have good control over vibrational wave packets, and so we are at a stage where we can really try to do chemistry with lasers, okay? This is other examples of sort of, molecular control with quantum light that have occurred in the last very recently. For example, I guess here there was some matter cooling with squeeze states. This one showed that you could have 2 frequency entangled photons which enhance the photon-photon transitions. This one is where you started out with a shape or some specific pulse of light, then you change its essentially frequency distribution and a few other things. So we have increasing capacity to tailor a pulse of light or to do well-tailoring of pulses of light. And so if you have an understanding of it and a modeling of it, then that could be done in an experiment. Okay. And so what you are going to do is really basically try to see whether we can study the vibrational properties and the vibrational modes and their dynamics in these molecules. Okay. Now, one way to describe these vibrations, basically, is just simple harmonic approximation. Basically, we have different number of vibrations for a molecule. For a general molecule with n number of, I guess, species here, or n, balls, if you wish, in there, you are going to have so many simple harmonic oscillators. And then if you want to go beyond harmonic approximation, you are really going to have a potential energy surface, which would be like this, which is like a Morse one, which will also have a dissociation energy associated with it, right? So to first approximation, we'll just take essentially non-interacting vibrations. So that's a problem which is fully solved, right? Because you already have basis states, you have everything. So what's the problem? Why are we doing it? And the reason we are doing it is because even though you have a solved Hamiltonian, that does not mean that all problems are tractable classically, or all problems are tractable in classical simulations, or all problems are tractable in polynomial time. So the major example of this, which sort of describes the complexity of simulating, pathways of bosons in some network, is so-called boson sampling problem. Okay? And so the idea is the following. So this is a specific example of H2S, H2CS, and it has a bunch of modes. For example, it sort of, it has a stretch mode, it has an antisymmetric stretch mode. This thing blobs up and down, or these things sort of vibrate these ways, basically. Okay. So it has a bend mode, a stretch mode, symmetric or antisymmetric, and then another stretch mode for this top part. And in general, you get 6 vibrational modes for this particular molecule. Okay. Now the question is the following. Suppose I excite one of this vibrational modes and the other vibrational modes. What's the amplitude for it to remain in those 2 states? Or what's the amplitude for these 2 excitations to end up in this mode and that mode, or whatever have you? In general, I have a waveguide, or I have a channel which has n pathways, and in that I put in m bosons. Then what's the amplitude of getting a particular distribution of the bosons at the outset? Okay. With 2 bosons, this is something that we learn, I guess, in basic quantum mechanics, right? If I put in 2 photons here, what's the probability of finding 2 photons here? Well, it would be the amplitude of going from this one to that and this one to that, plus, because of the Bose statistics, the exchange factor, right? And it would be the amplitude squared of those 2 terms. And that is what is called, so-called the permanent of this 2x2 matrix. If I have a 3x3 case, then I have to sum over all possible factors, all of them with a plus sign, basically, because these are bosons. And then for n-dimensional such cases, I will get a structure which looks like a matrix, but basically I'm calculating the permanent of it as opposed to the determinant of it, because it's all of them are positive sign terms. There are no cancellations. This calculation is a hard problem in the sense that the time required to calculate the permanent of an n-by-n matrix actually scales exponentially. Which means even though you know what is the bosonic structure, you know you have solved the Hamiltonian, it's a simple non-interacting bosonic problem, that does not mean you can efficiently do the calculations of what you would do in an experiment. Okay? And this problem has been known in the community as sort of, I guess, a boson sampling problem, which basically says calculations of permanence is hard. On the other hand, if you devise a chip like this, then you don't need to do the calculation of permanence. You can experimentally evaluate it. Just put in the bosons and let the nature do the calculation for you, which is the essence of quantum simulation. Right. Okay. So bottom line is, what we do is exactly this. And this entire sort of, all the stuff that I'll tell you from now on is doing this exact process. Now, there are a few more details here which I haven't talked about. And that is that essentially what's easy to visualize are these kind of, I guess, excitations where, maybe you just stretch this bond, which is what this arrow talks about. Or maybe you stretch this bond, which is what this arrow is. Okay? Or maybe you just stretch the top bond, which is what that arrow indicates. Those arrows, they indicate the wiggling of this particular H atom. Those arrows, those 2 red arrows indicate the wiggling of this one. Okay? And then it has one more sort of, I guess, excitation where both of these hydrogens move up together, basically. And those are localized excitations. Okay? On the other hand, the normal modes of this are shown in this center diagram, basically. Okay? The normal modes basically correspond to both of these hydrogens stretching together or in an antisymmetric manner, these wiggling also together or in an antisymmetric manner, and so on. Okay? So if we want to sort of study the behavior of these excitations, or more specifically, study or carry out certain simulations about what would happen if I excited, let's say, this bond and that bond, then what would I see as a function of time? That's the general question we are going to ask. What's the fate of a certain number of indistinguishable bosons which are being put into a different channels in here? What would be the time-dependent fate of them? Okay? All right. So this is, well, in the interest of time, I will just go over this. This just sort of shows you that there has been a lot of recent work which talks to how boson sampling is a hard problem and how experimentally implementing it is still fairly challenging issue. Okay? And so now I showed you this figure. The question is, how do we do this? Or how do we realize a unitary in which we can put in these excitations and then do a quantum simulation of these vibrational dynamics, right? Okay. And the way to do that is actually by a classic paper by Reck et al., which showed that any unitary, any discrete unitary, can be implemented just by beam splitters and phase shifters. Okay? Right. So in other words, on an optical bench, you can create any unitary in principle. Experimentally, it's far harder, basically. Okay? And the way you do that is, if I have M modes, something like this, then you first develop sort of, a Mach-Zehnder piece between the first and the second mode, and then between second and the third mode, and so on and so forth. So there is a systematic way of doing this, which in practice really just means that any unitary can be divided up into product of unitaries in 2x2 subpieces, which are just rotations and phase shifts, basically. Okay? And so you can do this in principle. Okay. And to do this in practice, what Bristol group did was basically build this chip. Okay. So now what you have is, instead of being on a optical table, you have it on some silicon dioxide wafer, where what they have built is a network of linear optical elements. And bottom line is, because of this, and you can find the details in this really beautiful paper by that group from about 3 years ago, and bottom line is, you can program the unitary in here. You tell me what 6x6 unitary you want implemented, and they can figure out what phases or what angles are to be supplied for it, and you can put that in a computer, and then this chip will dial to that unitary. On a physical basis, it does that because it has some phase shifters and beam splitters, which are sort of controlled by thermo-optic pads on top of this device and things like that. So it's extremely challenging engineering-wise, but once it is made and fabricated and tested, then you are able to realize any unitary you want, okay? Which is up to a size of 6x6. And that's why we have only focused essentially on doing quantum simulations of molecules where you have 6 vibrational modes, okay? Which by, Landau Lifshitz or whatever book you want to look at, essentially that corresponds to having, 4 pieces or molecules which have 4 atoms, okay? No, that will give you that. All right, so this is sort of the algorithm, if you wish, to use the chip, or what we need to do. You have a molecule, you have its vibrational modes, which are calculated using chemistry, quote unquote, basically. So you know all the characteristics. Specifically, you know the energies, and you also know the eigenfunctions, which is to say what is the weight which is associated, and the phase information which is associated with each of these stretches and bends that I mentioned earlier, okay? So you get the normal mode frequencies, you get the localized modes which are related, or the transformation from the localized modes to these normal modes, okay? And then you are sort of set to go, basically, right? So this is one example where what we are simulating is basically, let's say, the stretch mode of this. You take this molecule, which is H2CS or thioformaldehyde, and you pull on one of its hydrogen legs and let go and see how is it going to vibrate. So this one is showing the probability of it staying in its original mode, okay? And in this, everywhere, these sort of lines are the theory and or simulation, basically the theory calculation, and points are the experimental data. Yeah. So you get the probability as a function of time. Notice these times are in femtoseconds, which are the typical time scales for this, because these are all done with actual numbers, sort of, model-specific details. Okay. And then you could do this, or you could calculate some average probability, which is averaged over this time scale of 30 seconds, 30 femtoseconds, okay? Now, one of the cool things about a unitary chip, as opposed to a Hamiltonian simulation, is that time is arbitrary. Because you are dialing a unitary, you are not making a system and letting it evolve for a certain period of time. So you can simulate it to whatever time you want, basically, because all you want is actually to be able to dial the unitary, which we can't. And so you could do a simulation on a 30 femtosecond time scale, or you could do the same simulation on an order of magnitude longer time scale. This one is coarse-grained, but if you look at every one of those close ones, you get this sort of stuff. And you can do simulations on whatever timescales you want. What this means is also that you can sit arbitrarily close to, let's say in the case of PT, this means you can sit arbitrarily close to the PT breaking point where the timescales diverge, and it's all right. You can simulate Hamiltonian evolution across a transition where typically timescale diverge because it doesn't really matter. We are not making a Hamiltonian, letting it evolve. All you have is a unitary that you let evolve, or that you sort of dial in and do the simulation with it. Okay. Now, in this, the mapping is really that depending on where you put in the photon in this chip that I showed, corresponds to what sort of a stretch mode or what sort of a localized excitation that you are simulating in the system. So, for example, putting in photon in the top or the first waveguide of this chip would correspond to, pulling on this hydrogen, okay? Or basically putting in a photon in this chip, in this one waveguide would correspond to pulling on this hydrogen and things like that, okay? So now you could do a thing where multiple excitations are simulated, because instead of from the SPDC, the single photon sources, instead of having a single photon, you could have multiple photons, basically, and you can put that in, and that will carry out the simulation of having two excitations here, for example, and letting it, how do they evolve, or maybe having one excitation here and one here, and letting that evolve as a function of time. So in other words, you can controllably study multi-boson excitations or multi-boson vibrational excitations and the dynamics that it leads to. Okay. So these are some examples of it. For example, this is an example where we took, two singly excited modes. So this hydrogen and this hydrogen were pulled, basically. And then you look at what is the probability of it getting into different modes, basically. So the black one corresponds to the stretch mode. The blue one corresponds to the bend mode that I mentioned. And then this one corresponds to where these two hydrogens move up, which is like a stretch and a bend mode. Yeah. And in each case, essentially, this is more of a benchmarking because, these are calculations we can do classically. That's why we have theory lines. But what this shows is the appropriate control that we have at a quantum level, such that this process allows you to simulate the behavior of multi-particle excitations in the vibrational sector of a molecule. So this is an experiment with 2 photons which are put in 2 modes. Here is an experiment with 4 photons which were put in. So in other words, 2 photons put in this excitation, 2 photons put in that excitation, and then look at its time evolution. And as I mentioned, this is the answer. To calculate this, we need to calculate basically matrix permanence. And that is a problem which becomes harder and harder to do when you get systems larger, or the number of excitations which are there, vibrational excitations which are there, which becomes larger. So at this point, this is not, I guess, going over what you can do classically. But in near future, it can. Because building this device, this simulation, is where you are letting nature calculate the permanence, as opposed to you calculating it. And with classical computer, we cannot calculate it. We know that. These are some more examples of molecules where you're sort of simulating, do some excitation and look at how it evolves with time. And the point here is really that because time is a programmable parameter, we can sort of simulate evolution over, different time scales. This molecule has much longer time scale of typical excitation or oscillation. Over 100 femtoseconds, this one has risen halfway through just. This one, in 100 femtoseconds, you have sort of, maybe one oscillation which has taken place, whereas this HF, you already have a bunch of oscillations which are taking place over 100 femtoseconds. Okay? So this sort of shows you that you can do single particle and multi-particle vibrational excitations, basically, and their study very well. Okay? And this is all unitary dynamic simulations that we have done. In each case, these are all the data points, basically. Here, there is 2 dense data points to see the theory line effectively. Okay? But of course, we know nature is not that simple. Life is not simple. More specifically, we have other processes which are not described by just a unitary evolution. Okay? So for example, with water, these are the three modes of excitations that water has. There are these sort of bend modes, which are these hydrogen atoms sort of bending around. And then there is this stretch mode, which is the symmetric one or the antisymmetric one. Okay? Those are the excitation spectrum of water. Right? Those are those lines shown here. That's the ground state. And now if I excite one of these excitations, then in reality, that thing doesn't keep on going. Of course, it thermalizes because it mixes with the environment, interacts with the environment. And we would like to simulate that without having to go to a microscopic total unitary example where I have taken environment also into account, basically. And the steady sort of, standard method is use some sort of Lindblad equation with amplitude damping. Okay. Now, if you have done the theory of this, then you know that this Lindblad, when you carry out the calculation, gives rise to essentially non-unitary operators, which are called Krauss operators, which is what you need to implement, basically at the end of the day. Okay. And so the question is, how do I do simulation of a non-unitary using this sort of a unitary? And there is a trick to do that, the same one that we used for PT symmetric Hamiltonians as well, for which the experiments were carried out again using this same system, basically. And that trick is, take the non-unitary, scale it to some spectral norm less than or equal to 1, and then embed it into some sort of a larger unitary. So in other words, these Krauss operators, which are not unitary, they can form some upper block of a larger unitary that you can dial. And then by doing that, you are able to simulate this evolution as well by just looking at the appropriate sector of the model that you want to study. Okay. So we did that, and this is an example where, for example, you have one of the modes of this has been excited, so the black one, that is to say I stretch this leg of the hydrogen, okay, and then let it go, and I want to see how does that excitation sort of decay into, that excitation decay directly to the ground state, or that excitation decays into the other one, basically, because these are coupled things, or that excitation decays to the other one via this intermediate state. Okay? And this shows, basically this shows what you expect in a typical amplitude damping result. Things oscillate between states and then they die out. And this one is showing the occupation of the intermediate state, basically, which is this sort of a stretch mode, which has a low energy one, where things are going from here to there and then essentially going from here to there and then decaying or thermalizing. Okay? So this is sort of an example of basically showing that you can actually do non-unitary simulations of a non-unitary Hamiltonian or simulations in a non-unitary system, because it's a Lindblad equation, so it's not really Hamiltonian evolution per se. But non-unitary dynamics can also be simulated with a unitary dynamics by just taking that system and embedding it in a system which is twice as large. Okay? So because we have a 6-mode unitary, we can do sort of 3-side non-unitary stuff, basically, okay, at this stage. There are other things you can do, which are basically things like, for example, Anharmonicity. Until now I have been talking about essentially non-interacting bosons or non-interacting vibrations, but that's not true. If you take into account the interaction, basically, that at least in the mean field approximation, that gives rise to this sort of Morse potential. And what you can, now the question is, how do I then introduce interaction between photons? And what you are doing essentially is doing interactions which are simulating interactions by introducing nonlinear phase shifts between photons. So instead of just putting in 2 photons that you want to study, you put in another ancilla one, and then by looking at the state of the ancilla, you are post-selecting on it, you can just pick out the cases where the result has the phase shifts that you want. Essentially, that's what you're doing. Out of the many results that you get, you're just selecting out exactly the ones that have the nonlinear phase shift that you want. Okay? And so if you do that, then you get result, or you can do simulations of that as well, basically. Okay? So, for example, this is an example of, let's first focus on the left-hand side. This is an example where I excited water with 2 modes, or more specifically, I put in 2 excitations. One in this stretch mode of the hydrogen, the other one in this stretch mode of the hydrogen, and let go. And then I want to see what's the time evolution of it. And more specifically, what's the probability of these two excitations ending up in either both of them ending up on one side, or both of them ending up on the other side, or all other possible excitation matrix that you have. Okay? And this one is more or less a proof of principle, where it says there are situations where, because of symmetry, the interaction, the result with interaction and the harmonic approximation, those results are the same. On the other hand, there are cases where the interaction has tremendous effect because of the non-hermiticity, because of the, 1 minute, right? Yeah. The interaction has a lot of effect, basically. In this case, the solid line is the result from anharmonic potential, or this sort of interaction taken into account, whereas this dotted line is what would have happened if you did not have interaction. Now, this is not a solution, for all, because when you are doing this sort of ancilla work or nonlinear phase gates, then your efficiency has gone down, definitely, because you are only going to post-select on cases where these things work. So we don't really have a way to simulate fully interacting system. That's fine, but that's a task which I think nobody really knows how to do without really constructing a system which works like that, for the most part, at all stages. So this one is more of a proof of principle that at least some level of interactions where perturbation theory works is something you can do. Can I have 1 more minute?
Please.
All right. So the last part that I want to tell you about, which is quite exciting, I think, is what I told you about earlier, which was sort of pulse shaping as an approach to doing chemistry. And an old example of this is dissociation of ammonia molecule. Okay. So these are potential energy surfaces of the ammonia molecule. And these are potential energy surfaces for two states. One case, the lower surface, is where the system is in the electronic ground state. The top surface is where the system is in the electronic excited state. And so there are multiple pathways in which the ammonia molecule dissociates into, one hydrogen leaving, basically. Okay. And this is the parameter plane of the distance between this center and that is this axis. And this axis is the angle where, sort of the angle of the umbrella, if you wish, of the ammonia. So now you have ammonia molecule like that, and its angle can change. Okay. And this is sort of and what this had shown was that depending on which of these options you are choosing, there is an adiabatic pathway and a non-adiabatic, that is the one which is an excited state pathway, or so on. Okay. And so the question would be, is there some way I can have the system or have this chip learn and figure out and focus on a particular pathway? Let's say I want ammonia to be dissociated from, via this particular pathway or that particular pathway or many other pathways that it has. Yeah. Now, this has been, this is sort of related to pulse shaping, and that was tried out before. And so the process that you do is the following. You have these two, so suppose you want it to dissociate via this excited state pathway. Then what you do is you start out with some trial excited state wave function, which is a function of multiple parameters. Okay. In that, you put in the, and then simulate this dissociation, or more specifically what is the probability where the phonons get bunching into that particular bond. Because the way bond breaks is that one way to think about bond breaking is that the number of phonons in that particular bond is starting to diverge, just like spin waves destroy, let's say, ferromagnetic order by having many of them at small temperatures, right? So you try to maximize that. And because I'm running out of time, well, that is the process. So I think it's easy to sort of physically think about. You take a trial wave function, look at how many phonons end up in a particular bond that you want. You change the wave function a little bit. You look at, again, how many phonons end up, and try to optimize this way. Okay? So we did that, and what you find is that you start out with, now one of the things good here is that you are able to dial different unitaries very quickly, so you can do this actually. You start with a new wave function, which translates into some new unitary, and do that again and again and again, basically. And if you do that, you can basically show how to optimize a particular pathway in a dissociation process. Okay. For this small example, and here, for example, for every one of these cases, you started from random initial state, did 400 iterations, but usually this cost function, which is what you want to get, or negative cost function, you want to maximize, it gets maximized pretty fast. Okay? So this is a good way to do that. All right, so I think with that I'll sort of stop and won't really go over. I think for this community at least, and for me, a great interest has been that I have a quantum simulator which I can use to also study non-unitary systems. So with that, I'll thank you for your attention and take any questions.
Wide open for discussion, and given the time, we had to be, mindful of that, and maybe one or two very quick questions, please.
What sort of numerical method you use to simulate these problems?
So for example, if I want to simulate, the numericals is pretty simple because these are just properties of 6x6 matrices or permanents of whatever would be the Hilbert space, 6 raised to n by 6 raised to n, if I am putting in n excitations, n bosons. So it's just simple numerics that way, basically. It's just that the calculation of that is going to become harder. If you try to calculate a permanent of a 100 by 100 matrix, it's not too bad. But if you try to calculate permanent of 200 by 200 matrix, it becomes substantially harder, basically, okay? And so it's that wall that you are going to hit if you try to do many particle simulations like that. Okay, yeah. That's one of the reasons anyway, yeah. Yes.
So, just two brief peripheral questions. First of all, building on what you just said about the complexity of computing permanence, why is that so? Classical complexity of determinants is polynomial, no? It's a square, like n square or something like that. So why does it exponentiate? It's because the machine has to go and look for all the odd permutations and inverse the minus into a plus one by one, which takes n factorial.
I think that's roughly a good explanation. I can turn the problem around and maybe ask why a determinant where you have to add up n factorial terms in general is simple. And the reason is that determinant is basis independent, whereas permanent is not an operation which is basis independent.
Yes. Okay. Another peripheral question is, why do you focus on vibrational excitation? These molecules also have rotation bands, but is it because they are too dense levels? So for your computational reasons, vibrational spectra are easier to simulate in your...
Yeah, I think that the main focus has been on, in the experiments as well, the focus has been on how do I manage or investigate the vibrational modes, because that leads to bond breaking, and it's easier, or I guess it's experimentally of interest, one of the reasons at least. Yeah, no.
I just also wanted to ask the same thing. You have row vibrational things also, So in that case, and rotations will be extremely, extremely close spaced. So I think far more accuracy will be required because, yeah. Any further comments, questions, and things like that? Okay, let's thank Yogesh for a very vibrant lecture.